In example 2C, our system is 6x minus 3y is equal to 9, and 2x minus y is equal to 3. All right, so again, we're going to graph this. I will start with equation 1. Okay, so we will color code like normal. All right, so let's see. We've got 6x minus 3y is equal to 9. And I want to isolate the negative 3y so I can get the y by itself. So I'm going to end up moving the 6x over. So I will get negative 3y is equal to negative 6x plus 9. All right, and now to get y by itself, we're going to go ahead and divide by negative 3, but we've got to do that to all the parts. Okay, so we're going to get y equals negative divided by negative is going to give us positive 2x, and then positive divided by negative is going to be minus 3. Okay, so this is the equation of the first line in y equals mx plus b form. Now we can identify the slope and the y-intercept. So the slope is going to be the number in front of x, which is 2, and then the y-intercept is the other number, which is negative 3. Okay, so we will go ahead and graph this line. All right, so our y-intercept is negative 3, so look at the y-axis and find the point negative 3 on the y-axis. So there's your y-intercept. Okay, now we need to apply the slope. Okay, so one thing to notice here, the slope is not a fraction. Okay, because we're used to doing rise over run and it being a fraction. But you can make anything a fraction by putting it over 1. Okay, so your rise is positive 2 and your run is positive 1. Okay, so that means we're going to go up to right 1. Okay, so from this point, we will go up to right 1. And I'm just going to keep doing that, up to right 1. And I will do that until I fill out this grid. So it's going to be a lot of points. All right, and then I'm going to go in the opposite direction. So I'll go down to left 1 and just fill out the grid. Okay, so there we go. All right, so this line looks like this. All right, so here we go. All right, so this is our first equation. So the 6x minus 3y is equal to 9. Okay, and now we need to take a look at the second equation. Okay, so our second equation I will put in red. Okay, so we've got 2x minus y is equal to 3. Okay, I'm going to isolate the y, so I'm going to move the 2x over. So we're going to get negative y is equal to negative 2x. The 3 is positive, so plus 3. Okay, we want y, not negative y. So this is really negative 1 times y. So to undo that, we're going to divide by negative 1. So that means everything gets divided by negative 1. Okay, you could also multiply everything by negative 1. It's the same thing. Okay, so you're going to get y equals negative divided by negative is positive 2x. Positive divided by negative is negative 3. Okay, so again, well, you know what? I'm just going to stop here. Look at this. Okay, they're the same line. They're the same line. Both of these equations produced y equals 2x minus 3. They both have slope 2. They both have intercept of negative 3. They are the same line because they have the same slope and the same y-intercept. Okay, I'll even write that down. Okay, so the slope here is 2. The intercept is negative 3. Okay, so these guys are the same line. Okay, because they have the same slope and the same y-intercept. Okay, I'm not even going to graph the red line because it's the same thing as the blue line, but I will put on here, I will notate it that this is also the graph of 2x minus y equals 3. Okay, so now what? What does this mean in terms of the solution of the system? Well, both lines are the same. So you could almost think like, I don't know, I don't have, well, I guess I have a marker here. It's not exactly red. It's kind of pinkish. I have orange. Maybe I'll use orange. Like, if I came over here the other line would be on top of it. Okay, because it's the same line. They're going to lie on top of each other. Okay, I'm making too much noise. So I'm just trying to show you something here. So if you had the other line and you like put it on top, because they are the same line. Okay, so technically every point on the line is an intersection point, because the two lines, think of one line as being blue, the other one being red or orange, however you want to think of it. They are on top of each other. So they share, every single point on that line is common to both lines. Okay, so what we write for this, because every single point on the line is a solution, we're going to write that there are infinitely many solutions, because there are infinitely many points on the line. You can't count how many points are on the line. The line goes up forever in this direction. It goes down forever in this direction. So there's so many points on the line you can't count. So there's infinitely many solutions. Okay. Also, I want you to realize all these points that I have emphasized where I did my rise over run and I landed on a grid point, yes, those are points are on the line, but so are all the points connecting the dots. Okay, all the decimal x coordinates and y coordinates, they are also solutions to the system. Okay, so like for example, 2, 1, this point right here, 2, 1 is a solution to this system. Okay, what else? 4, 5. Okay, it's on the line. It's a solution to the system. Okay, down here, what is this? -3, -9. It's a solution to the system. You plug in x equals -3 and x equals -9 to both of these equations. Or sorry, did I say? You plug in, I meant to say if I didn't, -3 for x and -9 for y. Plug those assignments into both of these equations, you're going to get both true statements. Okay, so every single point, whether it's a big dot or not, is a solution to this system of equations. Okay, so what happens is there's a little extra step when you get infinitely many solutions. You have to do something called parameterize the solutions. Okay, so parameterize the solutions. Okay, and what that means is, because there's infinitely many solutions, you can't list them all out. You're going to write all solutions in a compact form. Okay, so the way you do this, okay, it's going to get a little more complicated when we have bigger systems, but for a 2 equations and 2 variables, it's not too bad. Okay, you are going to take one of the equations. They are the same equation, actually. That's why you got the same line. You're going to take one of the equations and solve for one of the variables. Okay, we already did that. Okay, we took both of the equations and we solved for one of the variables. We solved for y. You could have also solved for x. Okay, but we've already done this work, so let's use it. Okay, so what you do is you write all the solutions down in terms of a different variable that's not already involved in the problem. We usually use t to parameterize. Okay, and I'll even write that up here. Use the variable t to parameterize. I never know if I'm spelling this word right. Anyway, okay, so remember, the solutions have to be an xy pair. You need an x coordinate and you need a y coordinate. But we're going to write them compactly using a variable that's not already involved, which is t. Okay? All right, so again, here we are. These are both of the equations solved for one of the variables, solved for y. Okay? So when you look at this, okay, you ask yourself, which of these variables am I in charge of? Okay? You are in charge of x. Okay? You get to pick the x value. You can pick any number you want for x. And then whatever you pick for x, you multiply it by 2 and you subtract 3 to get the y value. Okay? Whatever you pick for x, there is a rule for how you get the y value. Okay? So the way we parameterize is, okay, I'm in charge of x. So we're going to call x t. Okay? And then we are going to write what the y coordinate is. Well, if x is t, then the y value is going to be 2t minus 3. Okay? This is a compact way of writing down every point on this line. Okay? So this is what you would have to write down. Anytime you get infinitely many solutions, you need to parameterize, okay? All right, so real quickly, I'm going to show you how this works, okay? This is what you would need to do, but I want you to understand that this generates all the points on the line, okay? So let me find a blank sheet of paper somewhere in this room, and I'll show you how this works, okay? So here's your parameterization, okay? So you've got t, 2t minus 3, okay? So pick a t value. You're in charge of t, okay? And then once you get that t value, you're going to plug it in to get the 2t minus 3 to get the y value, okay? And I'll even put that. This is the y coordinate. This is the x coordinate, okay? All right, I don't know. I'll pick 3 random numbers. I'll pick -3 for t. I'll pick 0 for t, and I don't know, 7, okay? All right, those are my t values. I'm going to plug each one in to this little formula here. So I'm going to get 2 times -3 minus 3. That's going to give me -6 minus 3. That's -9. Okay, so what that tells me is that xy, -3, 9, or sorry, -3, -9 should be a point on the line. Okay, and then I plug in 0. 2 times 0 minus 3. I get -3. Okay, so 0, -3 should be a point on the line. Okay, all right. 2 times 7 minus 3. 14 minus 3 is 11. Okay, so 7, 11 should be on the graph. Okay, all right. So if you go back to your picture, okay, these points are on the line. Okay, here's -3, -9. There it is. 0, -3. There it is right here. Okay, and then I'm a little off the grid, but if you look at 7, here's where x equals 7. Okay, you were supposed to go up 2 over 1, so this point would be a y coordinate of 11. Okay, so this would be 7, 11 up here. Okay, so this is just a compact way, okay, this whole idea of parameterizing, it is a compact way of generating all the points on the line, okay? I do want to mention, since, I've got you on this example, remember I told you to take one of the equations and solve for one of the variables, and we had already done the work where it was solved for y, but you could have solved it for x, okay? If you had, let's see, take one of the equations, again, they're the same equation, so just pick one, so I'll pick 2x minus y, 2x minus y equals 3, okay? We could have solved this for x instead. Okay, so I would have moved the y over and gotten 2x is equal to y plus 3. You want x, so divide everything by 2. So you would get x equals 1/2 y plus 3/2. Okay, that's a lot messier because it's got fractions, but it's still correct. Even though it looks different, it's still correct. Okay, so again, to parameterize, you ask yourself, based on this equation, which variable do I have control over? Okay, well, if I'm looking at this, I would pick the y, and then whatever I pick, I have to multiply that number by 1/2, and then take that result and add 3/2, and that would give me the x value. So you're in charge of y here. So the y coordinate would be the t value, okay? And then once you pick the t value, then your x coordinate would be 1/2 times y, but remember y is t now, plus 3/2, okay? So this is a second way of parameterizing the solutions, okay? They look totally different, totally different. This does not look anything like this, okay? But they end up generating the same points on the line, okay? So like, for example, I'll show you, okay? From this parameterization up here, from the initial one, we know that 0, -3 is on the line, okay? So, all right, if I want my y coordinate to be -3, for this parameterization, I would have to pick t equals -3, okay? And so then I would just plug it in, okay? So then I would get, 1/2 times -3 plus 3/2. Okay, that's going to tell me that -3/2, 1/2 times -3 is -3/2, plus 3/2, that gives me 0. Okay, so remember, this was the first coordinate, or the x-coordinate. Okay, the point 0, and then t is the y-coordinate in this case. 0, -3 is on the line. Okay, and you could have generated these other points. Okay, to get this one, you need to pick a t-value of -9. You need to pick a t-value of 11. Okay, it looks different, but it generates the same exact points on the line. Okay, you do not have to parameterize them in both ways. You just need to pick the one that, you know, is more obvious to you. Okay, so again, anytime you get infinitely many solutions, okay, which represents every single point on the line is a solution, okay, you have to parameterize the solutions, which means you're just writing all the points on the line in a compact form so that you could generate the points if you had to. Okay, let's try one more graph.